Good day, everyone. This is Chris back again with the Ancient Scholar. So we're going to continue talking about the periodic table of elements. We talked a little bit about groups and periods in the last video. In this video, I'm going to be talking about just the general classifications of elements. So the way that I look at this, and this is just very broad, the way I look at this is if you see kind of this orange area here, I'm going to circle it. Let's do a different color that kind of matches the orange. We'll pick blue here. Okay, so you see this kind of this orange area here, starting at boron, going all the way down to polonium here. So I'll just kind of shade that in a little bit. This area here kind of looks like a stair step. The elements in this are called semimetals. Okay, so these are the semi or semi-metals. And they're kind of the in-betweens. They're the go-betweens. They have some metallic characteristics, but they're not all the way. They're I guess they're sort of like the swingers in a way. They can kind of swing both ways depending on how you look at it. But they're known as the semi-metals or the semi-metals. Now, a really broad way of looking at the periodic table of elements, and let's find a color that will work. We'll go with green. Is everything to the left of that staircase. So all of this stuff here, I'm going to just kind of color that in here. So all of this stuff here, these are known as the metals. Okay, these are metals. Okay, with the exception of hydrogen. Hydrogen's kind of special, and hydrogen's kind of all by its lonesome there. Okay, so the semimetals, the semimetals, and the metals. Everything to the right. Okay, everything to the right of this staircase, all the way up to the group 8. So these guys, actually group 8 as well, can be included in this category. All these guys in here to the right of that staircase are known as the non-metals. Okay, the non-metals. So let's just go ahead and make sure we're good to go here. I'll use black. So this area here is semi-metals. Everything to the left of that, with the exception of hydrogen, it can generally be thought of as a metal, and then everything to the right of this can generally be thought as a non-metal. Okay, so this is actually very handy because metals and non-metals have very different characteristics for the most part. If you remember when we talked about the metals, when we were looking at the last video, when we were looking at things like lithium, sodium, and potassium, beryllium and magnesium and calcium and so on and so forth, they all had very small numbers of electrons in their valence. If we looked at, say, lithium here, I'll circle lithium. Lithium is in group 1, and that means that it has 1 electron in its valence. And if you remember, I talked about something called the Octet Rule, that says that atoms are generally happy if they can get 8 electrons in their valence shell. Well, if you can look at something like lithium over here, lithium it only has that 1 electron, and for lithium to meet its valence shell, it can either acquire 7 electrons. Okay, that could be a way of getting lithium to meet its octet rule, but I think of atoms as kind of like human beings, and they're lazy. They're inherently lazy. And I asked myself, well, if I was in lithium's shoes and I had 1 electron in my valence, I needed to get 7 to be happy. Well, would it perhaps be easier to get rid of that 1 electron I have instead of taking on 7? So if we look at lithium, lithium is in period 2, so there are 2 shells, okay, 1, 2, and I have 1 electron in the valence shell, the outer, and then I have 2 electrons in the inner shell. Well, if I get rid of that 1 electron in the outer shell, what does that leave me with? Well, that leaves me with the shell underneath that's left over, and it has 2 electrons, and basically I now have the configuration of helium. And if you remember from the last video, helium is very happy with 2 electrons in that first shell. So lithium is kind of now pretending to be helium, and lithium will be very happy because it got rid of that electron and it's met its octet rule, or we call it duet rule in the case of helium. Okay, let's look at something like magnesium here. I'll circle magnesium. Okay, magnesium is in group 2. It is in period 2, so just like, or period 3, excuse me. So 1, 2, and 3. And it is in group 2, so I have 2 electrons, okay, and then underneath there I have a shell. The second shell has 8 electrons, okay, I'll draw those in, and then the very first shell there, of course, has 2 electrons in there, okay. So if magnesium were to get rid of those 2 electrons, well, what would be left over is a shell that has 8 electrons in it, and magnesium would basically be able to pretend, like it was neon with 8 electrons in its valence. So this is very interesting. So one of the major properties of metals is that metals tend to lose electrons. They don't hold on to their electrons as tightly, because if they can lose their electrons, they can easily meet the octet rule. Okay, they can easily meet the octet rule. Now let's kind of look over here to the right, all the way to the right, and look at our nonmetals. Let's look at something like chlorine, for example. Okay, chlorine is in what group? It's in group 5, 6, 7. Okay, it's in group 7, and it is in period 3. So it has 1, 2, 3 shells, and if we look at its valence shell, it has 7 electrons. 7 electrons in its valence. Well, chlorine can do one of 2 things. It can either get rid of all 7 of those electrons, because the middle shell, the shell underneath, would have 8 electrons in it, or it could get an electron from somewhere, because all it needs is 1 more electron for its valence shell to be full, and it'd be happy. Well, again, atoms are lazy. The path of least resistance, at least the way I look at it, is it easier to get rid of 7 or to just add 1? Well, it's actually easier to add 1 electron. And we see that in all of our nonmetals for the most part. If we look at, let's say, oxygen here. Okay, oxygen is in period 2 in group, let's see, 5, 6. Okay, so I'm just going to draw its valence. So 1, 2, 3, 4, 5, 6. And it doesn't really matter how I draw the electrons for now, at least. So would it be easier to get rid of 6 or just to add 2, and then oxygen's valence shell would be full of 8? Well, it should be pretty obvious that it's easier for oxygen to kind of gobble up those 2. Okay, so what the general rule is that we can say now is that nonmetals, all these guys in here, nonmetals, with the exception of our noble gases, because their valence is already full, so they really don't bond. But the nonmetals in there, they tend to take electrons, and metals over here tend to give electrons. Okay, guys, as always, thanks for hanging in there.